Thank you very much. Copies of my slides are being handed out, so you don't have to take notes. I should start out by saying that the ideas and opinions I will state here are not those of my employer. American Scientific Affiliation will not take a position here, but they're rather coming out of my former career with IBM and some of the ideas I had over there. Okay. The two objectives of this talk are to assess the claims of what I call information apologetics and to seek clues to the origin of life. What do I mean by information apologetics? Just an argument that is circulating that is based on information for the role of an intelligent agent in the origin of life. In its most simple form, it can be expressed as a syllogism. Information must come from a mind. DNA is information. Therefore, DNA comes from a mind. Now, that's an oversimplified version, and the advocates are far more precise than that. You have to have the right adjectives here. Complex, specified information. You have to look at coded, non-coded, biological, non-biological. You have to be very careful in making these particular arguments. That's too many words to put on a chart, so this is a representative form, but it's also the version that usually comes out in radio and television and public lectures. It's the one that people remember, so it's kind of a placeholder here for that concept. So to assess this, we need to know a little bit about what is information and where does it come from. So I would ask you, what is information? And I would offer the broadest and most general definition as being anything that could be different. Anything that could be different. Last year, James Glick published his book, Information, The Information, a history, a theory, a flood, and in it, he cites as the first person to articulate a definition of information as being the vicar John Wilkins, who in 1641 said this: "Whatever is capable of a competent difference, perceptible to any sense, may be a sufficient means whereby to express the cogitations." I like that quote. A competent difference perceptible to any sense. It's probably one of the most concise definitions of information that is fairly comprehensive. So what does a scientist or engineer do with this? Well, it took about 300 years, but basically a scientist or engineer will say, all right, let's boil this down to the simplest thing that can make a difference. And Rolf Landauer put this in the form of a bistable potential well. Now, you don't have to be a fan of potential energy diagrams. You don't have to be a scientist to understand that if you roll a marble through two valleys separated by a hill, that it'll come to rest in one of two positions. No matter which one it comes into, it could be otherwise. It could be different. So if it could be different, there's information. If it couldn't be different, there would be no information. Now, basically in 1948, Claude Shannon, the Bell Labs engineer, then really put mathematical rigor to this and mapped out, and you already saw Casey on showing the equation, but in the thick seminal paper, Shannon has a full-blown integral articulation of information. But for our purposes, what we need to know is what Shannon pointed out is that what it comes down to is information is related to the surprise factor. Okay? What is the surprise factor? The greater the surprise factor, the greater the information. Very consistent with what Casey was telling you. It's all about probabilities. So remember that surprise factor. And then about 13 or so years later, in 1961, Rolf Landauer, IBM research physicist, made the probably the second most well-known step in information theory when he showed that erasing information, not generating it or processing, but erasing information required a minimal amount of energy, namely KT log 2. Now, that would be a lot of fun to talk about that, but for our purposes today, what we really need to understand is there is a thermodynamic aspect to information. Thermodynamics scares away a lot of people, and so we're not going to spend a whole lot of time on that, but you need to know that there is a fundamental thermodynamic context for information. So I would say that the baseline is a thermodynamic state that reflects all possible physical states, anything that could be different. And some have estimated that in the universe there are 10 to the 90th bits of information, about 10 for every elementary particle. Seth Lloyd estimated about 10 to the 120th bit operations, which is a little bit different. But it's vast. What it basically means is there's more information than we can deal with. So what we deal with is something that I call capacity. It is a set of targeted physical states. Take your iPhone. Thermodynamically, you've got enormous amount of information from a thermodynamic sense. You don't care about that. What do you care about? Well, you got a 16 gigabyte version. Well, that's the capacity. Or maybe you paid extra and got the 32 or the 64. That's the capacity of your iPhone. And you talk about that as the amount of information. Now, the syntax really refers to what's in those 16 gigabytes. Okay? What are the zeros and ones that are in there? Some of them you don't care about, and some of them you do. But what are the zeros and ones? And the semantics is really the meaning of it. What do those zeros and ones mean? And you never see the zeros and ones. You just see the text that comes out. Okay, so it's helpful to understand information in this text. And as Casey pointed out, word information is used in so many different ways that usually any blanket statement about information is incorrect. You need that qualifier to really understand what's where. Just to help put this in context, there's a linguistic example as an analogy to thermodynamics. In the linguistic example, you would have the set of all languages that are possible. The capacity would be, in this conference, we're using English. We have chosen a particular example of all languages in the world. The syntax is the actual words that are being spoken, and the meaning, or the semantics is really the meaning of what do all these words mean. So kind of keep that as something as a reference point. Whenever you hear or read anything about information, you got to keep in mind now what are they really talking about? Where is it? And one of the common errors is that people move from one level to another and didn't realize that they're talking about a different connection. Now, where does this information come from? What is its origin and where is it coming from? If you first take the thermodynamics category, essentially this is where you have conservation of information in the classical sense. That information is conserved like energy, like entropy. You get conservation laws here. So where does new information come from in this sense? It's primarily from quantum fluctuations, just like you see the potential for the generation of matter, the realization of quantum fluctuations. All right, so that's the backdrop, and that's not the primary focus of our concern today. Now, the capacity-wise, it's helpful to think of a term that Rolf Landauer used, which is information-bearing degrees of freedom, the IBDOF, which he used in his papers. Now, there's a good analogy on that in mechanical engineering, where you talk about structures and they have specific degrees of freedom or vibrational modes, and typically you've got an environment and energy can be transferred to and from different degrees of freedom. And you have something analogous to that in the information set, as Rolf Landauer pointed out. You've got the different information-bearing degrees of freedom, and information can be transferred from one degree of freedom or another to and from the environment. And that can be done, as Casey pointed out as well, whether it be through intelligent beings or by nature. This can be done in many different ways. Now, when it comes to the syntax, again, I think it's fairly clear from what we've talked about that information is such a ubiquitous concept here that individual bits can be set whether by intelligent beings or by nature. But what we're going to talk about today is what or who really determines a sequence of bits. This is where the interesting things come into play. And in terms of semantics, It's what or who determines the meaning of the bit. So this is where we want to concentrate the rest of our discussion today. Now, to do that, we first need to spend a minute here on the role of the mind. World Dictionary gives us the definition of intelligence: an aptitude in grasping truths, relationships, facts, meanings, etc. In other words, I would say an intelligent mind is capable of establishing and perceiving abstract relationships. And this is going to be an important consideration in the next few slides here. That kind of abstract relationships are those that are not necessary from a physical property or chemical reaction point of view. They require an intelligent mind to establish or perceive that kind of a relationship. Whereas a non-abstract or physical property or chemical reaction does not require a mind to establish. It exists as part of the natural properties. So let's keep that in mind, and let's now consider two examples. The first example will be English language example. The second one will be DNA. Now, if in the English language, and we'll focus on letters now instead of words, just for simplicity. It could be at different levels here. But let's suppose I'm communicating to you a series of letters in the English language, and the first one I put up then is, aha, the letter G. Now, consider the surprise factor. From Claude Shannon's point of view, what's the degree of surprise here? Well, there are 26 letters of the alphabet here. We've restricted ourselves to English. It'd be different if I had a different alphabet. But if I've restricted myself to that alphabet, then the surprise factor is 1 in 26. That's really 4.7 bits of information. So by designating a character, I've really provided you with 4.7 bits of information. Okay, fine. I'll give you another letter. Another G. There's another 4.7 bits of information. Now, what's the total amount of information I have now? Okay, I've got two instances of 4.7 bits of information. Do I now have 9.4 bits of information? What's my total? Well, it depends. It depends on your perspective of whether or not you forget the first one, or whether you consider any relationship between the two. Now, what is the relationship between those two? Is there any physical connection with them? No. Okay. However, any intelligent mind will perceive a relationship here. We see a pattern, and so suddenly the number of bits goes way up because the total number of possibilities is 26 squared rather than 26 plus 26. So the number of bits of information. So you see the complexity growing here, that how much information is there is very much dependent on an intelligent mind here. Okay. So it's not an objective kind of question with a simple answer. Now, let's keep going. Okay, let's go again. Hey, another G. Whoa, what are we seeing now? Okay, I'm starting to suspect something. Now we get to the fourth one. Now, look what's happening. The surprise factor is going down. What you've done in your mind already is saying, I'll bet you it's going to be another one. Right? And that means, according to Claude Shannon, the surprise factor has gone down. The amount of additional information has gone down. There's very little additional information. Okay? Now, the way Casey described it is that you've mentally inferred an algorithm that will predict it. So it's already predicted. And so the kind of information there, as he said, is Kolmogorov-Chaitin information. And it's algorithmic information. You could predict it. And so in that context, the information, but in another definition, in terms of the actual number of letters and the number of letters that are possible, okay, the information content has been the same. So it gets pretty convoluted. But here we can just go on, and it's G's all the way down. Wait a minute. That wasn't a G. That last one's a Q. Now that shot the surprise factor way up. Now, in fact, you added more information to just 1 in 26 because you called into question the entire algorithm. Okay? So it gets to be rather complex. Now, not to belabor this point too much, but if you then do similar to what Casey was showing, it's a random sequence of letters here. If you compare the two, and let's ignore that Q for a little bit, that makes the comparison a little harder. But if you have a very simple set and a very complex set, and complex is the right technical term here as opposed to the quantity of information here, but it's more complex, it turns out that in that sense, the top line has less complex information than the second one. However, neither one is very useful, which means that information per se is not a good measure of usefulness. And when you really look at usefulness, that's not really within the scope of information theory. As Claude Shannon specifically said, semantics are not within relevant to the engineering problem. Okay, but that's not totally true, because you have to look at there's a implication of there being a meaning. That's important. We've got to see that. Take a look at this. By now, if you're an anagram aficionado, you notice that second line could have been rearranged to give a word. Now look at this. In information content, it's between the top two. Okay? And why is that? Very interesting. It's far more useful than the other two, but it's got less information from a complexity point of view and more than the first. But there's nothing physical that made this significant. This is our role of our intelligent mind that gives more usefulness to anything else. Okay, keep that in mind. We'll use that as a comparison. Let's go on to DNA. Now, most of you know DNA. I don't have to give you too much, but in a 1-minute oversimplification of Biochemistry 101, you know that the DNA genome is basically a sequence here of nucleotides that we've symbolized here with the letters G, C, A, and T, etc. And the process is very complex and intricate, and essentially various RNA-based molecules will read, if you will, in the gene encoding section of it, a codon, namely a set of 3 of these nucleobases, and keep them in order here, and other RNA molecules will then translate that code into the corresponding amino acids, and at some ribosome, these get stitched together in the right order, and then you have a protein molecule that goes out and gets folded and does its work. How's that for a 1-minute summary of a physicist trying to talk about biochemistry? All right, so that happens for tens, if not hundreds of thousands of different kind of proteins that are there in a complex, and eventually what happens, they go out and do its different functions, and eventually the step is to create another copy of the starting genome. Okay? And that's kind of the consequence of all of the processes that are going on. Now, I want you to look a little bit. You see, of course, that there's a G here, just like we had in the previous slide. Think a little bit about these G's. They are symbols. It's a physical embodiment of a symbol of something. In the previous case, it was a symbol of the 7th letter of the English alphabet. In this case, G is a symbol of the nucleobase guanine. Okay? So both are abstract symbols in that sense. But now there's an interesting difference. Okay? That the 7th letter of the English alphabet is itself an abstract concept. Okay? Guanine is a physical molecule. There is a crucial difference that we have to keep in mind. Now, let's look a little bit more at the characteristics of DNA information. First of all, as you might have guessed, that there's a core characteristic here that DNA functionality is physical and chemical. The sequence is extremely important. There is no, as far as we know, or could be a little bit, but it's no dominant chemical connection that would order the nucleotides on a DNA. I mean, a G will follow a C or an A with very little preference one over the other. But the sequence is very important, as you see, because it determines what that protein is going to be. But at the end, all of these processes are chemical and physical, rather than in the English language, where it was our mind that produced the relevant relationship. And that's an important one that I want you to go home and think about, because it takes a while to think about that, because there's a difference between that kind of abstract relationship and the physical relationship. And I would suggest for your consideration here that in the DNA case, there's no evidence here that a mind is necessary to determine what the proper sequence should be. I would also suggest there's another aspect here, and that is the complexity of it. Because it turns out that we now know that the sequence of the nucleotides is not sufficient to determine the functionality. There's a whole range of epigenomic factors here that come in. But more than that, there's close connection to the environment, very much of what Steve was saying this morning. There is a very close coupling on the environment. Okay? And because there's a time sequence and a flow of information in terms of from the starting genome to the ending genome, the environment that influences it is generally not known at the time that the original starting genome was put in place. So I think there's much more than we can talk about in this short talk, but there's a lot of complexity in terms of when is there sufficient information to know whether you're starting out with a sequence that is sustainable. Okay. Think of the flow of information and the feedback, and draw those loops a little bit and think about the flow of information. And I'd say the functionality is highly complex, physical, and you really can't predict it at the time that the original genome is formed. That means to say even an intelligent mind is not adequate, may not be adequate to determine what that sequence ought to be, because the information is not available. So how does nature address that? What we see in nature is diversity. What I'm saying is that these kind of problems cannot be addressed from an individual case. And I think that's a major problem in any probability calculation, in any of these viability of protein calculations, that there's a tendency to focus on a linear path. You have to look at a population point of view. That's how nature works. And what we see is diversity around a probable solution. How does it work? The most probable solution is an exact copy of the original DNA, but you don't see that in nature. For one thing, it's not energetically favorable, but for the other thing, for survival, you have variation. And the variation is there because the environment is going to vary. Otherwise, it's not going to sustain itself. So these are the characteristics that we see as we observe the biology. Now, so given all of this, what can we say about information apologetics? Must DNA information come from a mind? I would suggest not necessarily. Well, for one thing, most information in the universe doesn't require a mind, but you may say, well, perhaps complex specified information in this case does. I would ask, however, where is the necessary causal relationship from intelligence to DNA information? I would suggest that no such necessary causal relationship has ever been identified. Okay. Simply being complex or specified or a code is inadequate. There is no necessary complex linkage. Most of the arguments supporting the information apologetics are inductive arguments, arguing that all of our experience with information systems is that they require an intelligent source. Yes, but what do human-designed information systems tell us about what nature can or cannot do? That's an inductive argument. You still do not have a compelling necessary causal relationship. In fact, these kind of analogy arguments, I like analogy arguments, they're illustrative in many cases, but they don't provide compelling logic here. And I would also suggest that even though there are remarkable similarities between human-designed information systems and DNA information, I would say far too little attention has been paid on the differences. And I would suggest to you that those differences are profoundly important to the question of origins here. And I would say that there are two aspects to those differences. One is that DNA functionality is physical and chemical, as we pointed out, and it's not really an abstract relationship where you might construct an argument that would be require an intellectual mind, but we do not see that in the DNA functionality. And the other aspect is DNA functionality is more complex. In terms of an intelligent mind being adequate for determining DNA sequence, I don't think we have a shred of evidence for that. Anything that humans have designed is so much simpler than the simplest biological system that I would suggest we simply have no reference point here. Plus the fact that I think the information is not there, even for an intelligent mind, to be able to determine it. I think if the principles of historical causal agency are correctly applied, that in the intelligent design hypothesis fails on all the counts. Not only doesn't the agency exist, but it isn't a unique hypothesis, and neither has it been shown to be adequate. Now, nothing else has been shown to be adequate either. I mean, that's why we're all looking for it. But it's still true that it is not really what we are led to from the evidence. We don't see a signature here that requires an intelligent mind. Okay? So what do we see? Well, if we look for the clues, our observations show that DNA information is generated by replication with variation. That is what we observe experimentally. We can also see experimentally that basic mechanisms of replication with variation occur in both biological and non-biological systems. We can't hide here behind chemical evolution versus biological evolution because the basic mechanisms are the same, and there's no principle in physics or chemistry or information theory that would say that there's a bridge here that you can operate in one or the other. What is different is that in the biological world, this replication is mediated through DNA and RNA-based biomolecules, and in non-biological systems, it isn't. That is a huge difference. Okay? As was pointed out in previous talks, we see self-assembly in non-biological systems that is very interesting. It's far simpler than anything you have in biology. There is still a huge gulf that has not been bridged. However, when you look at the signature, you see that common signature of replication with variation, which is powerful, and as far as I see, is the inference to the best place to look. That's where I'd put my research dollars in terms of the origin of life. Looking for a network of self-replicating, mutually catalytic molecules. We don't know of one yet. We've not seen it, but I know of no principle that would say that this is not possible. So what does that do to apologetics? Clearly, well, as Walter asked this morning, where is the theism in this particular viewpoint? In my view, God is everywhere here. The theistic aspect is in everything, not just in a difficult-to-detect esoteric view of origin of information, which we may be able to ferret out, but I think God's creative power is displayed everywhere here. I believe that God is the creator not because he may be the origin of information. I believe he is a creator because information exists. I believe he is the creator because nature exists. I believe he is the creator because science is possible. But most of all, I believe he's a creator because he lives in my heart.